shall we get going? I guess the sound bar, you can hear me well, right? So, good morning, everyone. Good to see you again. Welcome to this second day of our workshop. We're gonna start with the third technical session today. Format's going to be very much symmetric, similar to the ones we had last time. We're going to start with a headline talk. We're going to have three expert talks after that, with a coffee break in the middle, and then we'll wrap it up with a panel session, just like yesterday. And the theme of this session is on AI, grids, graphs, and networks. That's also the N in SpinCon as well. So then, for today's headline speaker, it's my great pleasure to introduce Stephen Lowe. He's a professor in the Department of Computing and Mathematical Science and Electrical Engineering at Caltech. Stephen has contributed major advances to internet traffic and congestion control, as well as semi-definite relaxation to power systems and optimal power flow in particular. He's received major recognitions. He's an IEEE fellow, fellow of the ACM and CSEE. And with that, the floor is yours, Stephen. Thanks for being here. Looking forward to your talk. Welcome.
Thank you very much. Okay, it works. Thank you very much. It's a great honor and a great pleasure to be here to celebrate Yoga's birthday and also 25 years at Minnesota. So I met Yogas much later than most of you. Yogas has a huge tree. And we met the first time in 2012. Yogas was presenting this beautiful paper by Hao, Hao and Yogas. And on multi-area state estimation, that was my first time meeting with Yogas. And I was presenting this primal geo algorithm for load control. So both looked at power system problems from an optimization perspective. So we talked, and then Yogas invited me to give a talk here. That was my first time visiting Minnesota after I switched to power systems. Thank you very much. So just a couple slides on why we are interested in what we do. If we look at the US, for example, it's similar globally. Energy use emitted 82% of greenhouse gases in the US in 2021. And if you look at energy use, pool activities, electricity generation and transportation, they emit more than 50% of all greenhouse gases in the US in that year. And they consume 65% of all primary energies. So primary energies are coal, gas, nuclear, hydro, renewables, and so on and so forth. And therefore, to drastically reduce greenhouse gas emissions, we have to electrify transportation, and in fact, almost everything as much as we can, and generate electricity from clean renewable sources. So I'll tell you a little bit of what we do in these two directions. And one of the things that emerged that becoming more and more important is what's called a distribution grid. So for communications, we have a backbone network and then a local network. So this is the local network in power system. Because a lot of the smart grid innovations first appear in distribution systems, and for many other reasons why distribution systems are becoming more and more important. So I'll talk about two things in distribution grid, optimization and learning. And for each one of them, Yogas and his team, his tree, have done really nice work that directly motivated ours. So I'll tell first of what's called optimal power flow problem, and why that is important and interesting results there. And then a lot of the optimization and control problems in power system, we assume we know the network, so we have a model of the network. And precisely what it means, we'll see later on. There's some mathematical model, and then we can design algorithms and so on. For distribution system, that's often not true in practice, and therefore we have to learn networks from some measurements. So I'll tell you a little bit about a really interesting idea, which is very unique among in this area, where Yogas and Vasilis and his postdoc proposed a very interesting idea of active probing to learn the network. That is really unique among the literature for learning power grid. And then I'll tell a little bit of some of our work in the same area. So hopefully I have time, I guess an hour. Then I'll tell a little bit about trying to cross the gap to implement some of the research that we've done. Okay, so the first piece, optimization. So distribution grids, unlike what's called a transmission grid, which is like the backbone, long-distance, high-voltage network, has two important structures. One is that almost all distribution network has a tree topology, what's called radial network. It means it has a tree topology. Secondly, it is what's called unbalanced three-phase system. Essentially, it means that there's a very important simplification scheme you can apply to power systems for analysis, for design, and so on, that you cannot apply. It's not accurate enough for distribution system. So that's unbalanced three-phase nature of distribution grid. So the way we model them, very simple. We have a network which you can think of as a graph with end nodes and some edges, and it's a tree. And each line is parameterized by a single 3x3, what's called series of admittance matrix. The 3x3 matrix, complex matrix. That is YJK for line JK. So for those in power system, we assume the shunt admittances are 0. If it is a single phase network, then the YJK is not 3x3 matrix, but a scalar. And each node has two variables. You can either look at the voltage phasor, Vj, which is a complex 3x3 matrix, and a nodal current injection, Ij, which is also a 3x3 complex matrix. Or you can look at instead Vj and Sj, where Sj is the complex power injection 3x3 matrix at node j. So these are nodal variables. So you can either look at Vj, Ij, or Vj, Sj. And Ij and Sj is related by Sj, so Sj is 3x3, is basically the diagonal terms of the outer product. So essentially, it's per phase, you take the voltage and the current injection complex conjugate. That's what it is. So the behavior of the network, this is steady state behavior, is described by this equation where at each node j, then Ij 3x3 matrix equals the sum of those Yjk, which is 3x3 matrix, Vj minus Vk. Okay? Or you write it in you stack all the variables up in 3n dimensional vector, then you get I equals Yv, where I is called the admittance matrix. It's a 3n by 3n for n nodes, complex symmetric matrix. It's not Hermitian, it's symmetric, and that's where a lot of the computational challenges arise. So this Y matrix is what we mean by a network. So in optimization algorithms, control algorithms, we often assume we know the Y matrix that describes the network, and in the second part, say, well, we don't know Y, but we have some measurements, can we learn Y? Right? So this model that relates I and V, we use in part 2. So in part 1, instead, we use the other model where we look at the relationship between V and Sj. Sj is a complex power injection described by this Vj, Ij. H is the Hermitian transpose, is a row complex conjugate, and then you expand this out, is that expression. But the important structure is that if you look at per phase, so this is 3x3, if you look at each of the three elements, Sj or phi per phase, then you can write that in terms of this quadratic form, VVH, where V is this 3n dimensional vector. So VVH is the realm 1 matrix. And those matrices, phi and psi j phi, are permission matrices, but not necessarily positive definite. And again, that's the issue. So you have a real part and an imaginary part. So that's the model. And what's called OPF, optimal power flow problem, they are fundamental in power system because numerous power system applications can be formulated as a certain OPF problem. And for almost all applications, the simplest form can be written as this non-convex QCQP. So this quadratic form, V is this, again, 3n dimensional vector, there's variables, and VVH is a rank 1 matrix. So it's non-convex because typically some of those CN matrices are Hermitian but not PSD. So that's the issue. And one can show indeed that OPF problems are NP hard and could reduce, say, subset sum problem, for example. Okay. And therefore, the two ways to solve this, at least, one is that you just run, say, interior points, so local algorithm, and how you will converge. The second is to look at a semi-definite relaxation. So VVH, you think of that as not a 3n dimensional vector, but 3n by 3n Hermitian matrices. So this is W. and therefore you can minimize over the W, subject to the constraint that W is linear, but also positive semi-definite. So it's a convex problem. You solve the convex realization, you check the optimal matrix. If you have rank 1, then great. Then you can recover an optimal solution for your original non-convex problem. Otherwise, it's not very clear what you do. You can do some heuristics. It's very hard to prove anything. So 2013, Yorgos and Hao and Emiliano had this really nice paper. And I think, as far as I know, the first paper that formulated the OPF problem on distributed systems, three-phase network, that formulated this as an OPF and proposed to solve this using the semi-definite realization. They also exploit the sparsity of the network and the causal structure of the network to come up with a distributed solution to solve this. Very nice paper. So this paper actually directly motivated one of our papers on distribution system. But I will talk about a different result, which is due to their very nice observation in their paper. So in general, if you solve semi-definite realization, there's no guarantee you will get a solution that has rank 1. But they made a very provide intuitive argument that why a rank 1 solution should be expected. So roughly, if you look at the feasible set, right, for a simple example, the feasible set is this ring without the interior, and semi-definite realization corresponds to minimizing the same cost, but over the feasible set with the interior, so it's convex. And therefore, if they have the same Pareto front, then you would expect that the optimal solution of your semi-definite realization is also feasible and therefore globally optimal. And indeed, that's what a lot of people found in practice. So we saw that in our own, so this is 2013, one of the upper E quarterly reviews. For those who have done upper E, it's extremely painful. So there's quarterly reviews. So there's some, we did some results. And indeed, if you solve SDP, often it's exact. You solve SOCP for tree network, it's often exact. Moreover, when we encounter cases where it's not exact, if you just run local algorithm, interior point, for example, often you converge to a optimal solution. And then there's a 2020 paper that looks at the largest set of benchmark test systems in power system for OPF. And they did the same thing, and they found that, again, almost always you get the realization is exact. And therefore, OPF is hard in theory, but seems to be easy in practice, in the sense that if you run semi-definite realization or convex realization, you often get an exact solution. If you run local algorithm, you often get a globally optimal solution. So, so I'll just tell you a result that attempts to provide some support for this empirical experience. So it's a work by a former PhD student, Fengyu Zhou. Okay, so he considered the problem in a very general form. You want to minimize a certain function fx, which is continuous convex, subject to a constraint, where the feasible set is compact but not necessarily convex. And convex realization is simply you take a convex superset X hat. So that's all you do. Very general, you minimize, so it's in the picture, so you minimize over the X hat, which is convex. The realization is exact if you solve the second problem, okay. If you solve the second problem, you get a optimal solution for the first. So that's realization is exact. Okay. That's a definition. If there exists a optimal solution of 2 that solves 1. Okay. But his result is basically, he derived a Lyapunov-like condition that will guarantee both. That if you solve the convex realization, you will get an exact result, and if you obtain a local optimal, it is globally optimal. So let me just state that result. So there are 2 concepts only. One is the path. So for every x, that is not feasible. That is in X hat, but not in X, right? So it's in the non-convex region, but not in a feasible set. A path is continuous function h, say from 0 to 1, where initially h0 is the point x, so this function h depends on x. You start from x, that is given infeasible point, and you end up with a point hx of 1 that is infeasible. That's a path. A path is simply a continuous function that takes a infeasible point back to the feasible set. That's a path, a continuous function. The second concept is a Lyapunov-like function, where it's like this figure, where v of x equals 0 if x is feasible, otherwise it's strictly positive. Right? And the condition, the first two conditions, is that for every infeasible point x in x hat but not x, there's a path. And also a Lyapunov-like function v such that both the cost f along the trajectory h x of t when x goes from 0 to 1, from infeasible to feasible. Along that trajectory, f, the cost is non-increasing, and also the Lyapunov function v is non-increasing. And you end up at a point that's strictly lower cost. Right? So if you give me a feasible point, there's a path that I can go back to the feasible set so that the cost is strictly lower. And along the trajectory, the cost doesn't increase, and the Lyapunov function value doesn't increase. There is such a path for every infeasible set, infeasible point. The second condition is just some regularity that this set of paths are uniformly bounded, uniformly equicontinuous. Okay, so compared with the standard Lyapunov function, typically standard Lyapunov function, we are given a dynamical system that specifies a path. And we want to say that that path is nice, it's asymptotic stable in the sense that that path will converge to some equilibrium point. That's what we want to show, right? And if we have a Lyapunov function where v of h is really positive, if it is not equal to the equilibrium point, is 0 otherwise, and also the path strictly decreases along the trajectory, along the path. Right? So then we are guaranteed that that dynamical system that specifies a path will converge. So in our case, we don't have a dynamical system. Instead, we have optimization. So this path is not specified. It's not specified by any dynamical system. So we just say that there exists a path, right? So in practice, when you apply this to OPF, you have to find that path. You have to define that path. So that's the tricky part. And the goal is to show that if we start with any infeasible point, we will end up with a point that is inside the feasible set with nice properties. Right? And the Lyapunov-like function is similar, that v of h is really positive if it is infeasible, and at the point that is feasible, at a feasible point, that's 0. And also the condition 1 in the previous slide essentially is similar, that the path, but also the cost, both of them does not increase. And then you show that these two conditions are necessary for those two nice properties. That if local optimals are globally optimal and relaxation is exact, then these two conditions must hold. They are not sufficient, so you need a slightly stronger condition, which essentially says that the path when you go from an infeasible point back to a feasible point is not only that it is a lower cost, but it has to be lower enough. That's essentially what that third condition. So that will be sufficient. Then you will guarantee you get those two nice properties. So you can apply this to OPF, to lower SDPs, and so on and so forth. So basically, if you have an optimization problem where the objective function is nice, the feasible set is non-convex. So that's typically the case for OPF. The objective function is typically convex, but the feasible set is not. Okay, so the second part. Okay, so I'm doing okay on time. So in this case, OPF, often we assume we know a model for the network. And what if we don't, right? So let me describe a really nice result. Again, as I mentioned earlier, it's unique in the literature in that it proposed an active probing to learn the network. So the network model that they use, Yilgaz and team use, is a linearized model where the voltage is a voltage magnitude or voltage magnitude squared. It depends on the model that you use. But it's some voltage magnitude. And then you can think of VT also to be the difference between successive voltages. So there's some details which are not important. But the important thing is that the voltage depends linearly on the injection P at time t, the real power injection at time t, and the reactive power injection at time t, Qt, and some measurement noise. So these RX matrices turn out to be positive definiteness. So it's a nice linear model. And what they propose is that suppose, because now we have more and more inverters in the network, and it's going to be even more going forward. And inverters are very flexible, controllable, and so on, and therefore you can actually inject small perturbations. So they say, okay, suppose you perturb PT a little bit by delta PT, and then you measure the corresponding perturbation on the voltage measurements, right? So delta V of t will depend on the delta P of t, where IP is an identity matrix where there's a 1 in the set of probing nodes. So you may not probe every node. So for the nodes that you probe, then you get this relationship. So these are the probing power injections, these are the measurements. So suppose we have this capital T 1, 2, 3 up to capital T measurements. You stack them up, you get a matrix which is delta V, which is delta VT for all the T's, all the peers, similarly for delta P, and then the noise. And then, among other things, there's a very nice set of papers, but among other things, they proved the following really very cute result. Supposing this measurement matrix delta P has rank which is the same as the number of probing nodes, then you can identify network topology if you probe at all the leaf nodes and you measure everywhere. If you don't measure everywhere, then there is a reduced network that you can estimate the topology of. Very nice problem that if you have partial measurements, how can you derive the topology of the network? So let me tell you the problem that we solved, which is very related. So recall this matrix in the previous part where this is a 3n by 3n complex symmetric matrix, right? And what we want is we have some measurements on I and V, partial measurements, and we want to figure out Y. So that's the problem. So suppose we have measurements at a subset of nodes. So these are the measured nodes, Vj voltage, nodal voltage, three-dimensional complex vector, and Ij nodal currents, right? And the remaining nodes are hidden, so we don't have any measurement. A key assumption is that where we don't measure, there's no injection. Injection is 0. Okay? And this is reasonable because whenever you have an injection, it means you either generate at the node or you consume at the node, and typically you put a meter. Internal nodes, there may not be a meter, but there's no injection. And therefore, I equals YV can be decomposed into this form where I1 is a set of the injections at a set of measured nodes, and 0 will be the hidden nodes, and similarly V1, V2, and then you have this block matrix. And if Y22 matrix exists, then you can take the third complement, which is this, right? And this matrix, Y bar, which is the third complement, is called the Cron-reduced emittance matrix, actually has physical meaning. It relates the measured injections and the measured voltages. So pictorially, you can look at this network, and if this is a hidden node, the yellow node, then the set of measured nodes will look like this, where its neighbors will be directly connected, and there's an injection, current injection at every node. These are the measured nodes. And the current injections on this sort of virtual network is related to the voltages on this virtual network by this Y bar. So Y bar is important. It means something. Okay. So our approach is 2 steps. Step 1 is just say, okay, I have measurements of I1 over some t periods and V1 over some t periods. Then I can do, say, some kind of a regression. And there are many different methods. This is just one natural way to say, okay, I'm going to choose a Y bar that will minimize the error of my measurement, subject to the constraint that Y bar is symmetric, and also it has 0 row sum. Okay, and there are also many other methods. There's a very nice recent survey, pretty comprehensive survey by researchers and team that looked at a lot of different works in single phase, three phase, tree network, mesh general networks, and so on. And so this problem corresponds to full measurement, right? So you have measurements everywhere, and then you want to figure out the matrix. And there are many methods to try to solve that. So step one, you do this, and suppose we have done that. So you get your measurement, you do whatever method, use whatever method, figure out the Y bar, which is the Cron-reduced network, Shor complement. And what we're interested in is, given Y bar, suppose it's true, Y bar, can you figure out the Y? Right, so pictorially, you have a network, in this case, a radio network. So the empty nodes are the hidden nodes. That has a admittance matrix, which is what we're interested in, is Y. If you look at the Shor complement, then you go this way to that way, right? So you eliminate the hidden nodes, you get a network that is, in this case, is the clique of measure nodes. And the corresponding Y bar matrix is this, and you want to go back, right? So you want to recover Y from Y bar without knowing the number or the identity of hidden nodes or the edges and so on. Okay. So when can you do that? Three-phase has extra difficulties. The key identification step needs to be a little more elaborate. But it is built on the first single-phase identification problem that you can omit Agatarian and also previous work with Claire Conlon. Okay, so all right. So mathematically, the problem is very simple. That given a complex symmetric Y matrix, 3n by 3n, suppose Y22 submatrix is invertible, then you can take a Shor complement, which you can think of as a map that maps Y to Y bar. And when will the inverse exist? And the answer is that if the underlying network is a tree, so given any complex symmetric matrix, 3n by 3n, you can define an underlying graph. For power network application, that is your network graph. If the network graph is a tree and there's some other conditions, then indeed it exists and you can compute it. Okay, so let me just tell a little bit what the other conditions are. Okay, so these are the assumptions. So the graph of your network, n-node network, is a tree topology is connected. And the second assumption is the key assumption we went through before, that the hidden nodes have zero injection. And then every hidden node has degree more than 3. So that's not important. If you don't have a degree 3, it means that you have hidden node connected to two nodes. Let's say those two nodes are measure nodes. You cannot differentiate between that and two measure nodes connected by a line. It's not critical. So these three conditions are required if you have single-phase problem. For three-phase problem, we also require this line admittance matrix, 3 by 3 matrices, to have positive definite real parts. And then this is a restrictive assumption, which I think is just a proof problem. I think it can be generalized, but the current proofs only requires this, where essentially it says that all lines are of the same type, they differ only in their length. That's what it says. Okay. Then you can identify exactly the Y matrix given a Y bar. Right? And the three observations, let me just, okay, yes, I think I have time. 3 observations. First is that Y bar has a very simple structure. That structure allows you to differentiate. So a Y bar network consists of all nodes that are measured, but some measure nodes are what we call internal measure nodes and some are boundary measure nodes. Boundary measure nodes means that it has some neighbor that is hidden. Internal measure nodes means that it's surrounded by other measure nodes. So using this graph structure of your Y bar, you can differentiate which nodes are boundary, which nodes are internal. And in step 2, then you can eliminate essentially the internal measure nodes, and then you can further reduce the problem to a very special case where the network has a single clique, meaning that the original graph is a tree, all the leaf nodes are measured, and they're connected by internal hidden nodes. So that's a very simple special case of the general problem. And then the key step is really, can you identify if your network is such a simple single click? So there's three. All right, so let me just one slide for each one of them. Essentially, the graph of Y bar has this very simple structure where it consists of a bunch of clicks that are edge disjoint and a bunch of trees. So it's simple to see in this case that the empty nodes are hidden nodes. So these two hidden nodes, if you do column reduction, you end up with this this graph for your Y bar, right? So you have three node, 2 clicks, and then a tree. And a node is boundary if and only if it is in one of those clicks. So it's a very simple structure. So that, again, allows us to reduce the general problem to a special case. So you can roughly, don't worry about the equations, but roughly, you can identify and then remove the internal nodes. And then you end up with a network that looks like this. There's no internal nodes. So a bunch of clicks, basically. They can be connected in different ways. The second step is just you extract them into individual clicks. So that's your special case. And the key step is to identify for each maximal click in isolation, can you identify that? So that's the key step. And then the remaining thing is just undo step 1 and 2. You just put them all together. So that's the second observation. The third observation is how do you do this? If you have a network that is a single click, can you identify the underlying Y matrix? And the key step is observation is that instead of doing a column reduction in one step, you break them into different iterations. So if you have 20 hidden nodes, so we don't know 20, but suppose you have, so the way to figure out the inverse is to try to understand the forward direction, right? So try to understand the column reduction process. So if you have 20 nodes in the column reduction, the forward process, we know we have 20 nodes that are hidden, and we want to do column reduction, reduce them. So instead of doing one step, you do 20 steps, where each step you will column reduce a single hidden node. And you, instead of looking at the sequence of the original matrix that you do iterative column reduction, you will look at a permuted matrix that has 3 properties. One is that it has an invariant structure in this permuted matrix that's preserved in each step of your column reduction. Secondly, each step can be reversed. And third, you can recover the original sequence from the permuted sequence. And therefore, you work with the permuted sequence. At the end of the column reduction, you can recover your actual column reduced matrix that you are interested in. But because every step in the permuted matrix is reversible or invertible, then you can go backward. So that's basically, okay. Also, I'm doing really well on time, so I will finish early. So let me tell you something that we try to deploy, some of the research that we do. Is many people contribute to this effort, and Zachary was one former PhD students. He was an undergraduate doing PhD now at Berkeley, and he was a PhD student, and a whole bunch of former students and postdocs and others. Okay, so World Energy Outlook, IEA, essentially, so scientists have been warning us about the climate crisis for half a century, and finally more people seem to be convinced. So it says that compared with 50 years ago, we have more tools that we can use, and the crucial step is to put these solutions to work. So that's the motivation. So we started to work on power systems around 2010, and we looked at OPF problems and stuff. So we looked at EV charging early on, 2013, and then as we all know, you prove theorems, and they're great. Sometimes we're lucky that some of them may be useful. And then in 2016, we started to build a test bed at Caltech and try to see if it works. That's a lot of work. A lot of work just to. So there was an adaptive charging network. So it was energized in February 2016. It's a 54 smart EV chargers, basically. So the idea is very simple. If you have 5 chargers in your garage, it doesn't matter what you do. If you have 50 or 500 chargers in the garage, then it's very important that you schedule them. Whereas the industry standard was everyone plugs in any time and they will charge at the peak rate. Right? And for workplace charging, there will be too inexpensive. There will be too expensive to build the infrastructure to support that, and it's also unnecessary. At the Caltech, for example, typically you can finish charging in 2 hours, but people park for typically 6 hours. So there's a lot of flexibility the industry was not extracting. By just do simple scheduling, then you can extract that value. Right? So that's the motivation. So by July 2020, that garage delivered 1,000 ton, some miles that corresponds to avoiding 1,000 tons of CO2 equivalent. Right. So we started a company. It's very difficult. Energy startups are much more difficult than IT startups or finance startups. It's very difficult. But in any case, so we started a company trying to commercialize that. And the value proposition is that if you have large-scale workplace EV charging that used to do this smart charging schedule, and you will drastically reduce your capital costs and operating costs. So we'll see a little bit of how concretely what that means. So it was acquired by EDF Renewables. Some of you might know, to basically build a business. And in 2022, it avoided 13,000 tons of CO2. So that's George. That's George and his brother. The night before, it was energized in 2016. And in some of the deployments. And that's the stuff that he built. So this is the prototype smart charger. So George is amazing. He's build gadgets. So he often show out former students. He often show out in my office and say, I build these gadgets. Usually it's interesting but not very useful. And then one day he comes in, I build this smart charger. So, oh, okay. So let's get some grant and try to build to see if it works. So the physical system that he built in the first garage was you have these 2 transformers and breakers and controllers and everything, and then the smart chargers that he builds. And the cyber system is very simple. So when drivers plug in their car, they use a mobile app to tell the system, I need 30 miles. I expect to leave at 5 p.m. So the system knows a lot more information than the industry standard. And then the information got sent to the cloud, and every 2 minutes, you form a simple convex QCQP, convex. So you can solve them, you do NPC, and then you use them to charge EVs in the garage. So this typically in real systems, optimality is not the most important thing. Even though we talk about optimization, really it gives you a structure to think about the trade-off of multiple factors, constraints and desires of different site hosts and all of those. All those factors, right? It gives you a systematic way to think about those factors. The actual optimality is probably the least important thing. And you end up with a product that is very flexible. You can adapt this to different desired preferences of the site hosts and constraints. They can be formulated either as part of the objective function or part of the constraints. Okay, so let me just show you some pictures. So this was the charging rate. So this is time, several hours over the charging rate. So there are say 40 curves, one for each EV, so you can adapt them. This is a demo in NREL where you have a building with some EV chargers. So this is the weekend. Not much happened, so you can see the dot curve. This is weekday, so you have still see a duck curve, but you have more load. And the goal is to control the EV charging so that the peak rate doesn't exceed a certain threshold. So that is important because for businesses, typically you pay for not only how much you consume, but also the peak rate, the peak power. That's called demand charge. For Caltech, for example, 2/3 of Caltech's electricity bill is actually due to demand charge, not the energy. So it's very important that when you install a bunch of chargers, that you don't blow up the demand charge. This is COVID. So this is a weekly pattern, 5 days, and then 2-day weekend, and then oops, everything's shut down. So let me just close with comments on the value that you can provide, right? One is the capital cost. So there are different incentive programs in California over the last several years where the utilities will encourage businesses and apartments to install chargers. So they will reimburse the cost. And when you add everything up, it's about, on average, it's about $15,000 per charger that the incentives will pay. Again, if you have 5 chargers, it doesn't matter. If you have 50, 100, 1,000 chargers in the LAX, for example, then it matters. So this is one of the PowerFlex early customers, 168 chargers, and it come to about $3,000 per charger. And you have different ways you can use smart charging to lower your operating costs. Four ways. One is you can reduce the demand charge by managing the load. Your site may have different time of use, that is time-varying electricity tariff, and you can charge in a way that will minimize your energy costs. When you do EV charging in California, you actually get carbon credit that has value in the secondary market. You can charge in a way that maximizes your value, for example. Or you can provide demand charge for your utility. So utility company will say, tomorrow 2 to 4, reduce your demand, then you can do that. Okay, so we built this as a test bed initially at Caltech. So we provide free charging, we encourage people in neighborhood to charge and all of that. And then after 2 years, it became a commercial operation that Caltech facilities will operate, so we cannot play with the network. So we built a software system on top of the physical system that provide 2 things, originally 3, but the PhD student ended up not doing the 3rd part for some good reasons. So 2 things, one is the data, one is simulated. Okay. So the data, this is 2020, there are more now, 53,000 charging sessions. So the session data is not only arrival, departure times, and the energy, but also every 10 seconds, there's a charging rate in amps for every car. So it's a fine-grained data. Everything's open, publicly available, and people use that for, say, monitoring user behavior, evaluate if a new charging algorithm, or if a pricing algorithm, or if you want to evaluate what is the flexibility of my garage, for example. Or evaluate if you have a whole bunch of smart garages on a feeder, what is the impact on the grid, for example. So this is, say, example user behavior. So this is the number of charging sessions. This is time. So this is when we start to charge, Caltech starts to charge money, payment. You have to pay to charge, then we see a drop. Then this is COVID, and so on. If you look at, say, the arrival time versus the energy delivered, the arrival time after COVID shows a greater variance because flexible hours. You can look at with or without charging, what is the amount of infrastructure that will be required. So it's a measure of how flexible your charging facility is. So the simulator. So the student built using real data and so on, built a very detailed model of the charging network, the local power distribution network that supports the smart chargers, the charger, the EVs, batteries, and other constraints, and so on. And you can use the actual data to drive your simulation as well as other signals, such as, say, the utility tariffs, say, the solar generation. You want to charge in a way that maximally utilizes your local solar generation, for example. And then there's the interface. So if you come up with a new charging algorithm, then you analyze it, and then you want to simulate this. Then as long as you interface with this simulator, then you don't have to implement any of those details. Then your charging algorithm can run on this realistic simulator, and so on. Okay, thank you very much. I will stop here.
Do you have questions for Stephen? Vasilis?
Yeah, thank you for the very interesting talk. I have a question on the Lyapunov path. The Lyapunov path.
Yes.
I haven't come down.
Or
repeat the question.
Okay, if I can hear it, yeah. The first part with the path, yes.
So, can we use it only analytically to predict the optimality, or can we use it also algorithmically to find the solution?
Okay.
Or inspire us to make an algorithm for solving the problem.
Right. So the question is that in the first part where we want to show that if you have a non-convex problem, you look at the relaxation, then when will the relaxation be exact and the globally local optimals are globally optimal, right? So there the conditions, the Lyapunov light function condition is that for every infeasible point, there's a path. There's a path. There's a path to go from the infeasible point back to the feasible set, along which the cause and the Lyapunov function doesn't increase. Right? So the question is that can you algorithmically compute that path, right? So in general, it's not clear. Not clear. So for specific OPF, let's say using the disk flow model, for example, then you can come up with that path. So just like this, the classical dynamical system Lyapunov function, figuring out the Lyapunov function is a challenge. And therefore, it's not very clear. Given a specific non-convex problem, you look at this and then come up with some way to find. And sometimes you come up with an analytical method to figure out the path. Sometimes maybe you can, there's an algorithm to compute that path. But in general, it's not very clear.
I'm going to follow up on that one. The condition that you told sufficiently that you need the increase of the cost function to be greater than some threshold. Is it for the numerical performance of solvers or both the intuition we have?
No. So okay. So the question is that the sufficiency. So the necessary. You have two conditions that is necessary, but you need additional condition. And the third condition, whether it is for numerical reasons. No, it's not for numerical reason. The third condition essentially says that along that, given an infeasible point, you want to find a path that go back to the feasible set, along which the Lyapunov function doesn't decrease, and the cost also doesn't increase. The third condition says that it has to decrease sufficiently. That is to avoid what Feng Yu, the former student, said is what's called he called it pseudo local optimal, meaning that if you look at locally, it is a local optimal. So, for example, in a region which is very flat, so you have a region which is very flat, the cost function very flat, and then it actually goes down. If you look at any point here, locally it's local optimal, but it's not. But you don't want this local optimal. You want it to come down. It is to avoid that. Yeah.
Also the conditions for the relaxation, if they are workable for problems with integer fire.
That result doesn't cover that. So everything is continuous. So the question is that the first part of the condition that said if you have integer variables, so the result requires it doesn't cover that.
Thank you for a very nice talk. I'm not an expert in the area, so it's very good for me to get this overview. So my questions may be a little basic. So in the probing of the network, this voltage, and so in some places voltages are functions of pi, so they're basically functions as mathematical objects. And then in other parts of the slides, there were complex numbers. So I was just saying a general question as to how time plays into probing the network. Are you like projecting these functions into something, or some basis or something, or are you using some special waveforms for this delta V or support? How time plays into it?
Sure. So the question is how time plays in the model, the power system model. So this is what's called a steady state model. So the actual, say, voltage and the currents on the network, power network, they are sinusoidal functions of time. Ideally, there's sinusoidal, the harmonics and all that, but sinusoidal. But we're looking at the steady state of your sinusoidal functions and interactions. So again, ideally, there's a steady state in which all the frequencies are the same and constant. In that case, you can look at the phasor. Because in that case, a sinusoidal function depends on only two parameters, the amplitude and the phase.
How about like when you're probing the network, do you probe, is it one probe or do you probe like one node at a time?
Right. Okay. So, the probe, actually, I shouldn't answer the question. Maybe Vasily should answer the question. So, but let me answer your time question. So, first of all, we look at the steady state. This is where the phasor, where the complex numbers comes in. They're all just complex numbers if it is just steady state. And then the time thing is, so this describes the power network at time scales of, say, minutes and up. Okay. And therefore, every 5 minutes, you can think of, again, conceptually, every 5 minutes, the network changes, for example. But within the 5 minutes, let's say, the network is just steady state, described by a complex number of phasors. And every 5 minutes, it changes, and then you measure that. So the time there is a discrete time of sufficient intervals in which you can just look at the steady state. I hope that answers your time question. The probing question, Vasily is here.
Last one, Jingdao.
Okay, so we have a question about the last piece of work on the network. My understanding is that you try to limit the peak power usage, right? Therefore, reducing the price. So I'm thinking, so this is for the LAN, right, local area network. So if you were to generalize this to the WAN, wide area network for, let's say, city scale or even larger state scale, we could deploy some global optimization, or we could do some distributed optimization. The LANs optimize their goals. So my question is, what would be the objective functions in that case for the wider area optimization? And second, if we were to do it like in a distributed fashion, what should be the architecture like? What would be the right signals, right? Pricing signals that we give the local area network so that the global utility can be maximized?
Okay, it's a very complicated question. We can stay here for an hour. So the question is that so the third part really is within a garage. That whatever optimization scheduling you do within the garage. So the question is that suppose you imagine you can have a city where you have lots of such smart garages. Within each garage, you can do something like this. But at a city level, or even multiple cities, let's say at the city level, you have, say, 50 such smart garages. You want to coordinate across different garages. How do you do that, right? Well, can you do that in a distributed manner? How do you price them? What will be the objectives, and so on and so forth? So indeed, there are work that look at these questions. And the idea is exactly what you alluded to, which is that these smart garages are actually extremely flexible and therefore valuable resources to help integrate renewables, and therefore to provide grid services. When we have more and more renewables, say rooftop solars and so on, and EV charging, so on, there's a lot more uncertainty and fluctuations in the grid, in distribution grid, that will cause what's called voltage instability problem. And therefore, these flexible and large loads are actually very important to stabilize the voltage. And therefore, there are work to exactly look at the question you pose, to say if you have these large flexible loads, which are, say, these garages, how do you coordinate them across a network to provide grid services to stabilize the voltage on the network? And then you can have different objectives, and there are issues that you raise that different garages may belong to different organizations, they may not share information, can you coordinate them through some kind of pricing schemes and so on and so forth? Yeah. So this can be done, but it's not a simple yes/no answer or ABCD answer to the question. Yeah.
Thanks.
Okay, thank you very much.